All right, welcome to another session where we are going to continue our discussion on basic differential equations and how they can be used to model growth and decay problems. Just get set up here. Oopsie. Now it's, in my opinion, nice to have a big picture idea of what is happening, what we're doing, what we're not doing, and how it's building up and the variety that we have seen. So our growth and decay problems so far have been a very basic exponential growth equation where the rate of change, the growth rate of the population, is proportional to the population size. Secondly, we flip that around to radioactive decay that had the same differential equation, but we now had a decay constant being negative, but the decay rate, the rate of change, is still proportional to how much of the substance of the material is left. Then we said, well, our basic exponential growth is fine up to a point where it then becomes a little unrealistic due to space limitations. So we changed the differential equation and looked at exponential growth with some sort of capacity built in, where the rate of change, the growth rate, was now proportional to the difference between the capacity and the population size. And we saw then that, yeah, there now is this capacity built in, that it approaches steadily, and it's a more realistic aspect at a late stage in the population's growth. So that was good. Then we looked at another decay situation, you can call it, with Newton's law of cooling. Those are O's, where the temperature changes at a rate proportional to the difference between that and some room temperature, let's call it T, or some ambient temperature, whatever the situation may be. And we looked at turkey cooling down, coffee cooling down, and so on. So number 3 and number 4 are very similar, and you can certainly make them look identical by building in, or by not building in, the sign in the proportionality constant is built into it. By sort of extracting that and always making the constant positive and manually putting a negative there, we can make them look identical. But we didn't do that for 1 and 2, so I didn't want to do that here. Today we're just going to do one more, and I'll call them concentration problems. And then the only thing that's left to do is look at uh, how do we combine 1 and 3 to a more realistic population growth model. But I just wanted to do a quick one today and add these concentration problems because they're not the same, as anything we've seen before, yet we still have a fairly simple differential equation. So let's see what these guys are like. Now, admittedly, I don't think there's any need to do this in general. I think by way of a couple of examples, we'll get the idea of what these models are doing, and we'll keep the example extremely simple. Of course, if we increase the complexity of the question, then the differential equation is going to adjust accordingly, and they can get complicated very quickly. So let's have a look at, for example, let me just resize this so that my camera is in view. Come on. Like so, perhaps. There we go. Let's look at 1443, 1444, and we'll get the idea. Mixture problems. I guess that would be a better name, right? Well, concentration is involved, the concentration, salt concentration, but I guess mixture problems might be a more appropriate name. Let's look at 1443. A tank initially contains 20 gallons of pure water. Brine containing 2 pounds of salt per gallon flows into the tank at a rate of 3 gallons per minute, and the well-stirred mixture flows out of it at the same rate. How much salt is present in the tank at any time t? And then how much salt is present at the end of 20 minutes? How much salt is present in the long run? Okay, fine. I'm going to need the function to answer those questions. Just the setup first. So let's get creative and draw a little picture here. So I can visualize what is happening. A picture always does so much good. Gives me time to just settle into the question and see what is happening. So, some stuff's coming in, some stuff's going out. In a way, to make it simple, 3 gallons per minute will be coming in, and the mixture flows out at the same rate. So that is very handy to keep things simple. 3 gallons per minute flowing in, 3 gallons per minute flowing out. So in the tank, I stay constant at 20 gallons. Now I want to know the actual amount in pounds of salt that I'm going to have in this tank. So let's define a variable. Let's say y represents the amount of salt in the 20 gallon, was it a tank? Tank, yes, tank. I suppose let's clarify that even further at time t, and t will be in minutes because that's the time unit that they refer to. In minutes. Okay, so now how do we come up with an equation that models, that describes this situation? Well, the amount of salt is changing because there's a salt mixture flowing into the tank, so therefore the amount of salt is increasing. And so I have a rate of change. So the rate of change in the amount of salt, or the increase in the salt amount in this tank can be calculated in two ways. First of all, it's represented by dy dt. Now let's keep track of the units here, which might be helpful. This is going to be pounds per minute. I'll do it like this. Pounds per minute. Because y is in pounds and time is in minutes. So now I have to make sure that the way I set it up, I preserve this unit throughout, this pounds per minute unit. And that's a way for me to check if I've done it correctly. So first of all, it's going to be salt coming in minus salt going out. Some salt's coming in, some salt's going out, but different amounts. Okay. Now, how much salt is coming in? Well, they say brine containing 2 pounds of salt per gallon. So 2 pounds per gallon. So now I have here pounds per gallon. I'm going to have to multiply that with gallons per minute to get the pounds per minute unit. So coming in, 2 pounds of salt per gallon at 3 gallons per minute will be 2 times 3. 2 for the pounds per gallon, 3 gallons per minute. So by keeping track of the units, I have that little help. So I'm just going to move this second term a little bit further out so I can have some space here. Now, some salt is being lost because of the 3 gallon per minute exit. So again, I'm going to need pounds per gallon that's leaving. And in order to get that as pounds per minute, I need to multiply that by gallons per minute to make sure my units are correct. So now what is leaving here? Sure, okay, the 3 is going to be the gallons per minute that is going out, sure. But how much here in pounds per gallon are going out? Well, I have in this 20 gallon tank, I have Y pounds of salt. So the per gallon amount is therefore Y divided by 20. Y pounds of salt in 20 gallons. So Y divided by 20 is the per gallon amount of salt. So there is our differential equation. Let's rewrite this to dy dt 6 minus, now the fraction is a little unfortunate, 3y over 20. And my initial amount, they say initially it contains 20 gallons of pure water, so there is no salt in the tank. So there's my differential equation. Now this one, I guess you could argue, is a little bit more complicated in that I need to put these terms together because when I separate the variables, that can only be done with multiplication and division. So I can't just move the 3y over 20 to the other side. That's not how it's done. It doesn't work. So I have to put these terms together over a common 20 perhaps. So I have 120 minus 3y. Then I'll take the 120 minus 3y to the y side, and 1 over 20 can stay, and dt goes to the right, and then I integrate. So I guess it's a little bit slight step in complexity up. I just have to be careful with my separation of the variables. Regardless, in terms of finding the antiderivatives, it's not really too much. I can guess and check my way through this. It's going to be the natural log of 120 minus 3y. Again, not worrying about the absolute values. When they eventually are, won't be an issue, just keeping it nice and simple. But if I leave it like this, then I'm not going to get exactly this target when I take the derivative. The derivative of this is going to be 1 over the something times negative 3. There's no negative 3 there. So I'm going to have to catch that negative 3 when it pops out. And 1 over 20t plus my constant I'll just put over there. So yeah, it doesn't look great, and we're running out of space, so we'll see how it goes. Now I will just get that negative 1/3 away by multiplying throughout by negative 3. So I'll get negative 3 over 20t plus, I'm going to number this constant C1 and then just update the constant. I know it's not the same constant, but it's still a constant. And for convenience, we really don't have to worry about what that constant looks like. Not right now. Then I'll do one more line. 120 minus 3y equals e to the negative 3 over 20t plus c2. And again, we're going to have a more convenient integration constant, as we have done many times before. Now let's just make sure we copy this over right. 120 minus 3y. 120 minus 3y equals me to the negative 3 over 20t. Negative 3 over 20t. And we now have the fact that I have nothing in the beginning. So if I plug in 0 for y, I'll show that there. I get 0 for t as well, making that exponential portion 1. This is 0. So m is 120 in this case. And I have to just isolate y to get a nice function, which we chose to not do this time. Plug it in. I have my general solution there. I can plug in the initial condition right away. Doesn't really matter. I have a 120 here as well, e to the negative 3 over 20t. And so 3y is 120 minus 120. Nice and convenient looking in this case because I had a simple initial condition. This guy goes to the other side, that guy goes over, and y dividing throughout by 3 will be 40 minus 40e to the negative 3 over 20t. Now I'm not going to factor out the 40 because it's not always going to be the same number. We have our function right there. And you see that it looks very similar, looks familiar, that our, where's my pen? Our salt is going to increase over time, but it's going to cap out at this 40 mark, starting at 0 in this case, going up to our 40. Now we can answer different questions here. Let's say how much salt is present at the tank at time t. Okay, fine, we've done that already. How much salt is present at the end of 20 minutes? So at the end of 20 minutes, we simply have 20 for t, and we calculate it. There's not much to it. Let's get that done. I'll just use the MathBot calculator in Discord. So 40 minus 40 times e to the power of, I'll put that in brackets, negative 3 divided by 20 times 20. Oops, my brackets did not go well. Let me just fix that 1 second here, like so. MathBot says, whoopsie, 38 point, let's go 0.1 if we round to 2 decimal places. So approximately, I can't get my p's to look right. Approximately 38 pounds of salt after 20 minutes. So we start with nothing. We put in a salt concentration mix, 2 pounds of salt per gallon into the tank at a certain rate. I also lose water at a certain rate, at the same rate, keep it nice and simple, and slowly the amount of salt in the 20 gallons increases, and at 20 minutes we have 38 pounds of salt. How much salt will there be in the long run? So let me back up a little bit here and say, and just check. This is a fairly beginner level discussion here, so I don't want to assume too much. You have a function like this in the box. How do you know what that looks like? How do we make it simpler and use our knowledge of transformations to see, well, how do I know what the graph looks like without a graphing calculator or some other help? One way we could do that to make a little bit more sense is to just look at the transformations of a simpler function that has the same look to it. Let's just say 2 minus 2e to the negative t. 2 minus 2e to the negative t. That still captures the same transformations without it being unpleasant fractions and all kinds of things. I don't really care about the scaling in there, or that much about the scaling in front of the exponential function. I'm just worried about the key transformations that I get. Because this we've done very early on, so we know how to handle this. If I start with now I'm going to do it in a lot of detail. If I start with my basic exponential function, like that, then I change my function from e to the t to e to the negative t. That is done by replacing t. I feel better if I label my axes here. Replacing t with negative t. What does that do to the graph? That flips it horizontally, reflects it in the y-axis. So let's try and have a decent graph backwards. Not always that easy. So I still have one y-intercept here, Still have a 1 y-intercept there. Now, what's next here? I could perhaps multiply the whole right-hand side by 2, e to the negative t. What happens to the graph? Well, not much. I'm just stretching it out a little bit. I'm not going to emphasize the stretch too much. I'll indicate. Oh, come on! I'm so wobbly this way around. So wobbly. I'm going to do it in little pieces. Not that that's any better. But my y-intercept is now at 2 because I've stretched it vertically. Then I will take that and multiply the whole right-hand side by a negative. The 2 and the negative are viewed as separate transformations for convenience. What happens now? That is a reflection of this graph, the previous graph, in the t-axis. It's a vertical reflection. So that is going to put it over here with the new y-intercept being at negative 2. Then I am done by simply adding 2 to the end, and that gives us the same original function. What happens to my previous graph? It's a vertical shift up, and now this horizontal asymptote becomes visible at 2, shift up. The y-intercept is, whoopsie, now going to sit at 0. Come on, buddy, you can do it. There we go. And there we see how it's approaching the added number, which in our example is 40, and it starts at 0. Of course, the left side doesn't matter because time is positive, and we get this graph shape. So long term, the amount of salt, or let's just say we're approaching 40 pounds of salt, but we'll never actually get there. It's just getting closer and closer and closer. That's sort of the capacity. The capacity due to the volume and everything that it cannot get. The closer it gets to that capacity, the more it slows down, which you can see in this original differential equation. Not quite, but I do have a capacity aspect here. You can see if I factor out, well, it's not quite clear what the capacity is from looking at the differential equation, to be fair. But if we look at the function version, it does have that same look as it does in the capacity exponential growth model. So admittedly, from the differential equation, it's not always clear exactly what the features of the function will be, but we solve the differential equation, and then we analyze the situation. Did we answer all the questions? Yes. Okay. So let's just do one more to get the hang of this. Let me make a new page here. New page for our new question, which is going to be extremely similar, just to solidify, what was this number? 1444. Solidify the concepts and the procedure for this slightly different question. Of course, there are many other questions we could do. One could make it much more complicated very quickly, but that's not the point for this introduction discussion. A tank initially contains 50 gallons of brine, in which 10 pounds of salt is dissolved. Brine containing 2 pounds of dissolved salt per gallon flows into the tank at the rate of 2 gallons per minute, and the well-stirred mixture flows out of the tank at the same rate. How much salt is present in the tank at the end of 10 minutes? Well, let's set up the situation. I really like a picture in this case. Just gives me time to get on top of what's happening here. Stuff's coming in, stuff's going out. Okay, I have a mixture problem. I'm going to let Y represent the amount of salt in pounds at time t, and time is, I think, again in minutes. Whoops, whoa, what happened there? Come back to me. In minutes, there we go. That's going to be in minutes. Okay, let's see what we have here. So I have 50 gallons in my tank. 50-gallon tank. Initially, I have 10 pounds of salt. Okay, so my Y0 is going to be 10. All right. Then I have brine coming in. It contains 2 pounds of salt per gallon. So 2 pounds per gallon coming in at a flow rate of 2 gallons per minute. 2 gallons per minute. And it's flowing out at the same rate of 2 gallons per minute. So I'm going to keep track of, let's say here, the net rate of change is going to be equal to the rate of change coming in minus going out, the rate of change of the amount of pounds of salt. So that's going to be dy dt, and my units will be pounds per minute. So I need to make sure that when I'm looking at the flow in, I'm looking at pounds of salt per minute. They tell me the pounds per gallon is 2 pounds per gallon at a flow rate of 2 gallons per minute. So therefore, 2 times 2 pounds per minute minus out will be, well, I need to find the pounds per gallon, and then I'm going to multiply that by the 2 gallons per minute. Pounds per gallon, well, in the 50-gallon mixture, I have Y pounds. So it's going to be Y over 50 pounds per gallon, the actual salt per gallon, times 2 gallons per minute flow rate. And there we have our differential equation. So dy dt equals 4 minus y over 25 will simplify, and our initial value is 10. There we go. Okay. Now, whoopsie. That's our differential equation. Before we worry about any other questions, we have to solve this differential equation first. So I will put the two terms on the right together over 25 it's going to be a nice 100 minus y for, excuse me, for 1 over 100 minus y dy and 1 over 25 dt. Integrate both sides. So I get natural log 100 minus y, but with a negative, 1 over 25 t with my integration constant. So natural log 100 minus y is going to be negative 1 over 25 t plus a different integration constant. So 100 minus y is going to be e to the negative 1 over 25 t plus integration constant, which I will rewrite to a different integration constant. I'm just making it look like, I'm just calling it m to make it a little bit more visually stand outish. E to the negative 1 over 25 t. Now, a little bit different to what we had before. I can solve for y first, perhaps. Y is going to be 100 minus m e to the negative 1 over 25 t. And then we can use the fact that initially I have 10 pounds of salt. So I plug in the 10 into my general solution, and that gives me my integration constant value. Whoops, I have not t here, I have 0 here, making that a 1. So m is 90. And so my function, my solution to the differential equation of the pounds of salt that changes over time is 100 minus 90 e to the negative 1 over 25 t. All right, so let's put that in a box here. Now, we don't have to graph this terribly accurately, but I do want to know where in this function is the quote-unquote capacity. It comes from this vertical shift in my transformations. It comes from this vertical shift in my transformations. So when I look at this new function, I see when I do transformations on this, if I really want to, the vertical shift that will happen is going to be this 100. So my capacity here is 100. I'm not starting at 0, I'm starting at 10. And there's my function. I don't have to look at these little bit more unpleasant numbers to understand what the transformations are doing to get the graph. Now, what are they asking? They are asking for how much salt is present in the tank at the end of 10 minutes. So after 10 minutes, we simply plug in 10 for t, and what do we get? Let's see. So I'm back to Discord. See the description if you are not on the Discord channel yet, where we discuss and you can ask questions. I'll just use the MathBot to show the calculation in chat as well. We have 100, just looking at our function, minus 90 times e to the power of, I'll put that in brackets, so feel free to follow along as we go. Negative 1 divided by 25 times 10 minutes. Every time I do not go back into my bracket. Man, let me just fix my brackets here. That looks good. Can we actually see this in chat? We will in a second. 39.67. So we are over here somewhere. Oh, we're not even close, right? We're over here somewhere after 10 minutes, 39-ish. So it's a little bit slower because the tank is bigger, to be fair, but you get the idea. So this is going to be, oh, come on, stupid line. This is going to be in pounds, approximately, or just under 40 pounds of salt we have after 10 minutes. But we know from the function that we are slowly, the amount of pounds of salt slowly increasing to try and reach this 100. It's a hard cap. It'll never actually get to 100, and the closer it gets, the more it slows down because where's my tank here? The initially what's coming out of the tank has a very low amount of salt. So I'm gaining salt rapidly. But the more salt in the 50 gallons, the higher the concentration and the more salt is exiting to the point where they are matching each other almost perfectly. And the actual increase in the amount of salt gets really, the graph gets really flat. So the actual increase gets very close and closer, in fact, to zero. So with this, we've introduced, let me just go to the top here. We've introduced over the last 5 videos uh, a nice variety in our introduction to growth and decay problems. We have one more left, and it's unfortunately a big one, where we will combine our basic exponential growth, which is really good for initial growth, really accurate rather, and we're going to combine that with exponential growth with a capacity, which is really good at the end where space becomes an issue. And so we'll see, okay, what happens when we combine those two to get a more realistic model. But that will have to wait until next time.
Please remember to click the like button if you enjoyed the video and to subscribe if you want to be notified of more videos. Thank you.